Hello students, welcome to the classroom point. In today's session, we shall discuss the carbonyl compounds. So carbonyl compounds means the compounds having the carbon double bond oxygen group is called as the carbonyl compound. So in this carbonyl compounds, carbon always participate in the sp2 hybridization and having the planar shape with bond angle 120 degrees. These carbonyl compounds are of two types. They are called as aldehyde and ketone. So in the carbonyl group, carbon connected with oxygen through double bond and it has two other free valencies. So within those two valencies, if one valence is fulfilled by the hydrogen, such groups are called as the aldehydes, and if both the valencies are occupied by the carbon, they are called as the ketone. Now let us see the preparation of the aldehydes and ketones. Let us see from the alcohols topic first. So from alcohols usually an oxidation gives the respective carbonyl compounds here. Now let us see primary alcohol, secondary alcohol and tertiary alcohol. So in these alcohols, primary alcohols on oxidation gives the aldehyde with mild oxidizing agents, and with the strongest oxidizing agents they give the carboxylic acids that we shall discuss what type of the oxidizing agents are to be selected. Secondary alcohols always on oxidation gives the ketones. Whatever the type of the oxidizing agent it may be, secondary alcohols gives only the ketone. And tertiary alcohols generally do not participate in the oxidation so that no product happens. But under the drastic conditions, means if you apply the high temperature and the pressure, then there is a breakage of the carbon-carbon bond, so which provides the ketone. Now, usually during the oxidation of these alcohols, no oxygen is to be added, but hydrogens are to be removed. So, generally, this oxidation process is like a dehydrogenation process. Now, if you say the primary alcohol, this is a primary alcohol RCH2OH. On oxidation, there is a H2 molecule, removal of the H2 molecule from the hydrogen from the carbon and hydrogen from the oxygen, both are to be removed and a double bond will be developed. Hence, primary alcohols always gives the aldehydes on oxidation with mild oxidizing agents, as they are having the two removable hydrogens, one will be removed and other still stay with the carbon. But in the case of the ketones, the carbon is connected to the, in the case of the ketones, formation of the ketones, they are formed from the secondary alcohols. So in the case of the secondary alcohols, carbon is connected to the two carbon groups and with one hydrogen, and OH is having the one hydrogen. So on oxidation, there is a loss of H2 molecule. So within that hydrogen, one hydrogen from the carbon and another hydrogen from the oxygen will be removed, and a double bond will be developed between these two carbon and oxygen. So it is called the second ketone. Now, tertiary alcohol, such type of the things are not possible as there is no removable hydrogen on the carbon. But under the drastic condition, there is a breakage of this carbon-carbon bond. Hence, there is a chance for the formation of the ketones, but usually no reaction occurs with the oxidizing agents in the case of the tertiary alcohols. Now, the question arises whether all type of oxidizing agents of primary alcohol gives the aldehyde or any other thing. Actually, primary alcohols gives the aldehydes only with the mild oxidants, and with the strong oxidizing agents, primary alcohols will give aldehydes initially and later carboxylic acids. Now let us see the type of the oxidizing agents that are to be used for the oxidation of the different type of the alcohols. So here acidified or alkaline KMnO4 or K2Cr2O7 potassium dichromate, and CrO3 dipyridine CH2Cl2, PCC pyridinium chlorochromate, PDC pyridinium dichromate, DMSO dimethyl sulfoxide, manganese dioxide, cetic ammonium nitrate, AgNO3, copper 300 degrees centigrade, copper with 300 degrees centigrade. So all of these to be used for the oxidation of the alcohols to provide the carbonyl compounds. And among all these carbonyl oxidizing agents, and here this particular one, first one, H plus means alkaline or acidified potassium permanganate or potassium dichromate or strong oxidizing agents, which usually converts the primary alcohols to the carboxylic acids, but rest of the oxidizing agents they convert primary alcohols to the aldehydes. Secondary alcohols always will give ketones with any of these oxidizing agents, and within these the specialty is there with some oxidizing agents like dimethyl sulfoxide, which converts the primary alcohols to the aldehydes, secondary alcohols to the ketones, and it even oxidizes the primary alkyl halides to the aldehydes, secondary alkyl halides to the ketones. And manganese dioxide preferably oxidizes allylic alcohols and benzylic alcohols to the aldehydes and ketones. Cetic ammonium nitrate oxidizes the primary alcohols to the aldehydes, whereas aromatic methyl group also will be oxidized to the aldehyde group. And AgNO3 preferably oxidizes only primary and secondary alcohols. And AgNO3 is so selective reagent that even if the secondary alcohol is fully crowded, then it shall not be oxidized. It oxidizes only primary alcohol in such cases. Copper with 300 degrees centigrade converts the primary and alcohols to the aldehydes, secondary alcohols to the ketones, but tertiary alcohols will be giving the alkene molecules with the copper and 300 degrees centigrade. So now let us see some of the general examples. So this is the primary alcohol is giving the aldehyde, primary alcohol giving the aldehyde with the PCC, PDC. You can use any of this. This is a secondary alcohol with H plus KMnO4 or H plus K2Cr2O7 gives the ketone. But in this case, copper with 300 degrees centigrade temperature. Let us see a different type of the alcohols and their oxidizing property. Primary alcohols gives the aldehydes, secondary alcohols gives the ketones. This is a dehydrogenation process, and tertiary alcohols usually gives the alkene. If this type of the tertiary alcohol is taken, whatever the length of the chain it may be, the carbon-carbon double bond will be developed between the OH group and next highly substituted carbon to provide the stable alkene molecule. Now let us see the opener oxidation. Its reverse reaction is called as Merwin-Pondorf-Verley reduction, MPV reduction. So in this case, we take the secondary alcohol and acetone. Acetone means you can take any ketone, usually acetone or cyclohexanone. So which is oxidized in the case of the aluminum isopropoxide or aluminum tertiary butoxide. So if you take the secondary alcohol will be oxidized to the ketone, and acetone whatever we have taken will be reduced to the isopropyl alcohol, and its reverse reaction is called as a Merwin-Pondorf-Verley reduction. So here you can see, and the importance of this oxidation is it will not disturb the unsaturation. If any unsaturation is there, it will not disturb but oxidize only secondary alcohols to the ketones. This is one such example here. Now what does it mean by isopropyl alcohol? This isopropyl alcohol, you remove one hydrogen so that we get the isopropoxide, which is carrying the one negative charge. So this isopropoxide formula can be written as there are two CH3 groups. So CH3 taken twice, CH is there, CH I have written O minus. So this is isopropoxide with one negative charge. We know that aluminum carries plus 3 charge. So to neutralize 3 charges, we need this type of the groups. So the same groups I have written here and put the 3 here. This is called aluminum isopropoxide. Its original structure is like this: aluminum connected to the oxygen, this oxygen, later CH3. Like that, 3 such groups are there. And aluminum tertiary butoxide means this is the tertiary butyl alcohol. Again, you remove one hydrogen from here, you will get the tertiary butoxide. And tertiary butoxide formula we can write, there are 3 CH3 groups. So CH3 taken thrice, CO minus, CO minus. So again here it carries one negative charge, aluminum carries plus 3 charge. So that to neutralize this plus 3 charge, we need 3 such type of the group. So this is that molecular formula, and the structure is like this. So when you take the secondary alcohol with cyclohexanone or aluminum tertiary butoxide or isopropoxide, this secondary alcohol part will be oxidized to the ketone, and this ketone will be reduced to the alcohol, and no unsaturation gets affected. These are all that examples. Then how to get the carbonyl compounds from carboxylic acids? Carboxylic acids on reduction gives the aldehydes. No ketones will be produced in this type of reaction when carboxylic acids are directly reduced to by lithium aluminum hydride or sodium borohydride. And apart from this lithium aluminum hydride, sodium borohydride, why? Because I had made a separate video on this. I'll leave it in the cards here. You please check that. And we will discuss a different unusual reducing agents, that is calcium hydroxide, alumina with 400 degrees centigrade, manganese oxide with 300 degrees centigrade. Now the question is, we know that calcium hydroxide, here I am taking the calcium hydroxide which is a base, and take the acetic acid, which is an acid. So acid reacts with the base and forms this salt that is called as calcium acetate. So calcium acetate structure is like this. This calcium acetate on heating means a distillation process. So there is a loss of the CaCO3 molecule. So Ca, calcium here, carbon here, three oxygens. It looks like a kidney shape. So CaCO3 molecule and this CH3 shall be connected over here so that you will get the CH3CO, CH3 ketone. And if you take the calcium formate, again you remove the CaCO3 so that it gives the formaldehyde. So if you take the calcium formate combination, you are getting the aldehyde part. When you take the calcium acetate combination, you are getting the acetone part. When these two are mixed together, then which molecule we will get? Again combine these two and heat it. So here there is a loss of the CaCO3 here, and here also there is a loss of CaCO3. This is the calcium acetate part and this is the calcium formate part. So after the loss of the two molecules of CaCO3, here this CH3 molecule, CH3 part shall be connected over here so that we will get the CH3CHO aldehyde, and this CH3CO part shall be connected to this hydrogen so that we get the CH3CHO. 2 moles of aldehyde we get, and apart from this, and there are a chance for the formation of this CH3 can also connect over here to give the acetone part CH3 C double bond O CH3, and there is a chance for this hydrogen to connect over here to give the formaldehyde. So it is not compulsory or it is not clear that we will get only aldehydes. There are chances for the formation of aldehydes with this calcium acetate or calcium salts of carboxylic acids distillation. Then what about alumina? Alumina means here we take the normal carboxylic acid and formic acid. So when a carboxylic acid combined with the formic acid in the presence of the alumina at 400 degrees centigrade, we get only aldehydes. So whatever the alkyl group is there, this COH group shall be connected to the CHO group. But only aldehydes we don't get the ketones in this case. If you want to get the ketones alone, then take the carboxylic acid and treat with the manganese oxide 300 degrees centigrade. It gives the only ketones. Now, hydrolysis of the geminal dihalides. So in the hydrolysis of the geminal dihalides means if a carbon is having the two halogens, they are called the geminal dihalides. When these are subject with the aqueous KOH, these two chlorines will be replaced by the OH groups. So we get the two OH groups. Whenever two OH groups are placed on a carbon atom in the organic chemistry, the molecule is unstable. Immediately it will be leaving one water molecule. So there is a loss of one H2O molecule and carbon-carbon double bond will be developed, and here we got the ketone. If you want to get the aldehyde, then replace this R part with the one hydrogen. So again, these two chlorines will be substituted by the OH groups, and there is a loss of H2O molecule. Again, we get the aldehydes here. Now, ozonolysis. Regarding the ozonolysis, I had made a separate video, and here just I am revising the concept. I'll leave that concept also in these cards in this area. You just please check that. So in ozonolysis, alkenes and reductive ozonolysis gives directly carbonyl compounds, means it may be ketone or aldehyde, that depends on the type of the alkene we select. If double bonded carbon is having at least one hydrogen, that part will give the aldehyde. If it is not having the hydrogen and both are carbons are there, then they give the ketone. So here during this, just to disconnect this double bond and put oxygen in the presence of the ozone, zinc followed by the zinc H2O. So we get the aldehydes here. Now this alkene part, if you see, carbon-carbon double bond is there, alkyl part and alkyl part. Here hydrogen alkyl part. When this is subject to the ozonolysis, means reductive ozonolysis, just to disconnect the bond and put oxygen both the sides. So this part gives the ketone and this part shall gives the aldehyde. And apart from that, there is one more oxidizing agent part, that is NaIO4 or periodic acid or lead tetraestate. In this, NaIO4 or HiO4 is called a Lamiax reagent and not lead tetraestate. The use of these reagents is they convert the diols to the carbonyl compounds. Diols in the sense of glycols. When two OH groups are placed on the side carbon atoms, adjacent carbon atoms, then the bond between those two carbon atoms will be broken and these two carbon atoms will be converted to their respective carbonyl part. Not only that, even alkene parts shall be oxidized just like ozonolysis part. See here, we will take one example. Here there are two OH groups placed on the adjacent carbon atom. Use HiO4, disconnect the bond. Since hydrogen is there on this carbon, it will be converted to the aldehyde. If there is no hydrogen, only carbon atom is there, one more carbon, then this shall be converted to the ketone. And apart from that, if you take the alkenes, then alkenes shall be converted to the aldehydes and ketones, just like ozenolysis process. Break the bond and put the oxygen on both the sides, you will get the respective carbonyl groups. Next, with CrO2 Cl2, chromyl chloride. So alkenes on reaction with the chromyl chloride, on oxidation with the chromyl chloride, they give the carbonyl compound. So in this particular case, the least substituted double bonded carbon shall be oxidized to the carbonyl carbon. We will see here, this is a alkene molecule which is oxidized in the presence of the chromyl chloride and in the presence of the CH2Cl2. So this particular part, which is having only hydrogens, no carbon, this is the least substituted carbon, will be oxidized to the aldehyde, and this will be reduced to the CH group. And here both are having the alkyl group, so there is no chance. So one shall be oxidized to the ketone, and there is a migration of the methyl group to the side carbon atom, gives this type of the ketones. Now we shall discuss the hydroboration oxidation. So hydroboration oxidation of the alkenes we shall discuss now. So alkenes and hydroboration oxidation, they give the alcohols of anti-Markovnikov's category. So that video also is there. I leave it in the description box. You just go through that video. Complete discussion is there. Hydroboration oxidation of the alkenes, how they are providing the primary alcohols. So these primary alcohols on oxidation gives the aldehydes. So this process we have discussed, as primary alcohols are giving the aldehydes, and what type of the oxidizing agents are to be used, means except H plus K2Cr2O7 or KMnO4 or OH minus K2Cr2O7 or KMnO4. Rest of all oxidizing agents, they just convert the primary alcohol to the aldehyde. And from alkynes on just acid hydrolysis, they give the carbonyl compounds. And in this, if you take the acetylene on acid hydrolysis, it initially gives the enol, which undergoes tautomerism and gives the aldehyde. And rest of the alkynes, whatever the type of the alkyne it may be, on acid hydrolysis they give the ketones. So only alkyne that gives the aldehyde is acetylene. Rest of all type of the alkynes, whether it may be terminal alkyne or internal alkyne, they give only ketones. Now, let's discuss the hydroboration oxidation of the alkynes. So, in this case, if you subject the alkynes to the hydroboration oxidation, they initially give a trialkene substrate boron, which on hydrolysis with the H2O2 OH minus, they give the enol and gives the aldehyde. So, here alkynes, terminal alkynes on hydroboration followed by the oxidation gives the aldehydes, whereas internal alkynes gives the ketones. But in the case of the alkenes, they give hydroboration oxidation, they give the alcohols. Alcohols and oxidation gives the ketones are carbonyl compounds. But in the case of the alkynes, separate oxidizing agents are not necessary. Why? Because in the case of the alkynes, there is a formation of the enol which undergoes tautomerism and finally giving the respective carbonyl compound. Now, how to get the carbonyl compounds using the Grignard reagent? So, Grignard reagent on reaction with the esters or cyanides, it gives the respective carbonyl compounds. If you take the hydrogen cyanide, it gives the aldehyde. If you take the any other alkyl cyanide, it gives the ketone. The mechanism is like this. I just take the one mechanism here. So this is hydrogen cyanide, partial negative charge lies on the nitrogen, partial positive charge on the carbon. Here carbon magnesium bond is ionic bond, so carbon gets the negative charge, magnesium gets the positive charge. So this negative charge will attack over the partially positive charged carbon, replaces this pi bond. So pi bond will be shifted over to the nitrogen, and we get this intermediate product, which on hydrolysis gives the aldehyde. And whereas other cyanides, they give the ketone. Why? Because apart from the hydrogen cyanide, if you take any alkyl cyanide, here there will be CH3 group or any alkyl group. So that alkyl group reflects over here, and the same alkyl group will reflect over here, which becomes ketone. And esters on reaction with the Grignard reagent followed by the acid hydrolysis also gives the ketone. If an ester is from the formic acid, then we get the aldehyde, and if ester from the normal other than formic acid, then it forms the ketone. So we shall see here this is the methyl formate. Grignard reagent attacks over this carbonyl carbon, replaces the methoxy part, gives the aldehyde. And if you take the excess of amount of the Grignard reagent, so Grignard reagent will attack over again on the carbonyl compound aldehyde, giving the secondary alcohol. And again, if you take the still excess amount of the Grignard reagent react with the alcohol, giving the alkane molecules. The same can be observed in this case. Rosenmund's reduction. Rosenmund reduction means acid chlorides on reduction in the presence of the palladium barium sulfate, sulfur, quinoline, and xylene, they give the aldehyde. Ketones cannot be prepared by this method. So you take any type of the acid chlorides, they just give the aldehydes. If you want to prepare the ketones from the acid chlorides, so Rosenmund's reduction is not suitable method, but other methods are there. Means you need to subject these acid chlorides with the other organometallic reagents such as lithium tritertiary butoxy aluminum hydride. This is the reducing agent, and similarly tri-N butyl tin hydride, this one. So if you subject acid chloride with any of these reagents, you'll get the aldehyde here also. But if you same compound is subjected with the, so if acid chloride subjected with the these two reagents, we get the aldehyde. And if sodium aluminum hydride or diisobutyl aluminum hydride, diol H, reduce the esters to the aldehydes. So these are all preparation of the aldehydes. Now ketones, if you want to prepare from the acid chlorides, as I just said now, these are to be subject with the organometallic compounds. Here it is a Gilman's reagent, that is dimethyl cadmium. So this methyl group replaces this chlorine. So will occupy this particular position. Since here two methyl groups are, so we are taking the two acid chloride groups. So we get the acetone, and these two chlorines from the two molecules will be connected to the cadmium and giving the CdCl2, cadmium chloride. And from nitriles. So nitriles means cyanides on the SnCl2 and HCl followed by the acid hydrolysis give the aldehyde. This is called the Stephen reduction. And apart from the SnCl to HCl, even you can use the diol H, which converts the not only esters to the aldehyde, but also cyanides to the aldehydes. This is an aldehyde. Now, Walker's process. So, in this Walker's process, alkene on reaction with the PdCl2, palladium chloride H2 in the presence of CuCl2 and air or oxygen, we get the carbonyl compound. Here, what type of the carbonyl compound is produced depends on the type of the alkene we select. If you take the ethene molecule, you will get the acetaldehyde, but other all type of the alkenes, they give the ketones. And the next one, the last one is from alkyl halides. So just I said already, in the case of the oxidizing agents of the DMSO, dimethyl sulfoxide on oxidation of the primary alkyl halides gives the aldehydes, secondary alkyl halides gives the ketones, and it will not oxidize the tertiary alcohols, so that no reaction takes place. Dear students, hope you understand my explanation. If you understand, please do not forget to subscribe the classroom point. Thank you.